This worked example explores ways to assess and design compounds in 3D using the SeeSAR Pose module. The compounds in this example have been generated as part of a virtual library and are being considered for further optimization. The crystal structure displayed here shows the binding site of heat shock protein 90 with enalaspib as the co-crystallized ligand. Enalaspib is a selective potent HSP90 inhibitor that displays a long duration of anti-tumor activity. The beta-resorcinol group forms a tight hydrogen bond network in the binding site, but the pyrazinol methyl isoindoline does not form any strong interactions with the protein. The virtual compounds are all based on an amide coupling reaction with a beta-racinoic acid core and commercially available secondary amines. In StarDrop, open the file SeeSARPose.stproj by selecting Open from the File menu. On the left, in the SeeSAR area, the protein HSP90 is displayed with its secondary structure and the co-crystallized ligand enalaspib. The dataset on the right contains 10 compounds from the library that we will analyze in 3D. To do this, we're going to generate a set of conformations using StarDrop's SeeSAR Pose module. However, if you wish to use third-party docking software for such a task, then StarDrop's Pose generation interface can be used to connect seamlessly to your chosen platform and retrieve the docked conformations. From the Go button menu at the bottom of the SeeSAR area, choose Generate Docked Poses. This will generate poses for the entire dataset. To generate poses for individual compounds, select these rows in the dataset first. When generating poses, we need to define a binding site. By default, you will see that the co-crystallized ligand enalaspib is already selected, and we will use this. Note, if we had already docked other ligands, then we could use one of these to define the binding site instead. If you have the SeeSAR affinity module, then the Estimate Binding Affinity option is also checked, but we are not going to use this here. Click the Generate Poses button to start the process. You'll see that a new column is added to the dataset in which the FlexX score for each compound will be displayed once the poses have been generated. While the calculations take place, the compounds will be listed as either being running or queued. Once the calculations have completed, you'll see that each compound has 10 poses generated, as shown in the top right corner of the structure in each row. To view some of the poses that have been generated, select the compound in row 3. This is now loaded into the 3D viewer alongside the co-crystallized ligand. To view the binding site in more detail, select Show Binding from the Binding menu. From the Display menu, choose Display Options. In the Display Options dialog, tick the Show Protein Surface option and choose Transparent and Color by Log P from the menus. Close the Display Option dialog. To see any pose in isolation, simply select it in the table below the 3D viewer. While the docking scores provide us with a qualitative idea of how we might rank order the compounds, we'd like to combine this with more information about other compound properties. Select the Scoring tab. In this example, we have created a multi-parameter scoring profile to reflect the range of properties we'd ideally like to see alongside the docking score for an oral, non-CNS target. Run the scoring by clicking the Go button. Note that you will see a message telling you that the docking score has no uncertainty associated with it. Ideally, all the data we score should have an appropriate reflection of the error, and we know that the docking scores are not always accurate values, but in this case, click OK. This generates a multi-parameter score for every compound and adds it to a new column. The score is a value between 0 and 1 and reflects the probability of the compound being successful given the criteria we have defined in the profile and the data available. A perfect score would be 1. Each score is accompanied by a histogram which gives a quick visual indicator as to how each of the compound properties contributed to the score. The lower the bar, the more of a problem that property may be for the compound. We can examine this in more detail in Card View, where we have already created a card design that shows the overall score alongside the docking score and the HERG PIC50. Click the Card View button near the top of the right-hand toolbar. We can see in the second compound down on the left that the bar in the scoring histogram associated with HERG inhibition is shorter than the others, indicating a potential problem. From the property values shown at the bottom of the card, we can see that the predicted value is 5.8, whereas in our scoring profile we indicated that an ideal compound would have a HERG PIC50 below 5. On that card, click on the HERG PIC50 property to display the glowing molecule. The glowing molecule highlights regions of a compound that are having a significant impact upon its predicted properties. Regions of the molecule increasing the predicted value are coloured red. regions decreasing the predicted value are coloured blue, and regions having no overall influence are coloured green. The colours are interpolated between these extremes to reflect the influence of that region of the molecule on the property prediction. We can see from the glowing molecule for our chosen compound that there are a number of regions glowing red, indicating that they are increasing the predicted hERG affinity. However, we should consider these alongside the 3D pose to consider their importance to the compound's ability to bind to the target protein. Click on the SeeSAR tab to return to the 3D viewer. We can see from the glowing molecule that the resorcinol group is bright red and increasing the predicted hERG affinity, but we can see from the 3D viewer that this group is critical to the target binding affinity. In particular, we can see that the isopropyl group is very red, but this binds into a hydrophobic cleft, and so we probably wouldn't want to change this because there is a significant risk that this would disrupt the binding. On the other hand, the hydroxymethyl is also quite red, and we can see that this is a lot more accessible. As such, making changes in this region may enable us to improve the hERG prediction without having an adverse effect upon the binding. We can use the Edit mode in SeeSAR Pose to try out new ideas and get quick feedback about how the changes we have made may affect the binding. Click on the Edit switch at the bottom of the SeeSAR area to display the 2D editor. Here we can use StarDrop's standard editing tools to make changes to the displayed structure. The selected structure will be used as a template for the newly edited structure to be docked into the same site. In the Sketch area, use the Bonds tool to change the hydroxymethyl into a carboxylic acid. To specify an element, hover over an atom and type the element symbol, in this case O. As you edit the compound, you will see a message saying Generating Pose below the 3D viewer, and a new pose will be displayed within a few seconds. To compare the new compound with the original, tick the Show Template option below the 3D viewer. We can see that, in comparison to the original compound, the overall binding conformation has been maintained quite well, and that the carboxylic acid forms an additional hydrogen bond with a target, which may assist the overall binding. As such, this may present us with a viable alternative, which we will add to our dataset. From the Go button menu at the bottom of the SeeSAR area, choose Add Pose to Dataset. On the new card, you can see that the hERG PIC50 is now below 5, due to the addition of the carboxylic acid. This decrease is supported by the glowing molecule, in which the carboxylic acid is coloured blue because it is decreasing the predicted hERG affinity. Click the Table View button on the toolbar to switch back into Table View. Click the Edit switch to come out of Edit mode. If you scroll across the table, you can see that the score, along with all the predicted properties, has been added to the dataset along with the new compound. The overall score is faded to indicate that there is a missing property, in this case the docking score. These are not automatically calculated because they take a lot longer to generate, but it can be added easily by selecting this compound and running pose generation as we did earlier, selecting the co-crystallized ligand as the reference once again. As further steps, we might wish to consider a more quantitative estimate of the binding affinity. This is something which you can do with the SeeSAR affinity module, as demonstrated in the next worked example.